All right, the next issue for us to get into is when we're going to mix quantifiers. So I want to talk a little about having a for all and a there exists statement in the same line. And so what I want to do is I want to think about a statement that says for all x, there exists a y such that x plus y equals 3. This is the example from our course notes. And so what I want to do is I want to think about what does this mean? And specifically, I want to pay attention to the order. We're always going to read from left to right. The reason why I say that is that that's the choice that you're going to make for the quantifiers as well. So what this says is that, I'm just going to write it because I think it's important enough. For all x, let's say our domain, by the way, is the real numbers. Make the domain whatever you want if you don't want it to be the real numbers, but say for all x, there exists a y such that, so these parentheses, you say is such that x plus y equals 3. So that's what this condensed statement, that's what that says. For all x, there exists a y such that x plus y equals 3. And I want to notice that you pick x first. So what this is saying is that no matter what x you start with, you can find a y such that x plus y equals 3. This statement is true. So this statement is true. And to show that, imagine that you pick some value of x. Well, if you pick some value of x, how can you pick y? Well, you pick y to be 3 minus x. And then if you add x to y, you get 3. So I'll let you verify that that's true, but this says that no matter what value of x you start with, you can always find a y such that x plus y equals 3. Okay, so that's the first thing. The second version of this is going to be the opposite. And again, if you want to say, I guess let's just make this, well, the x plus y is the same as y plus x. So switching x and y is silly, but just to keep it, just to put this, there exists statement first, we want to consider the statement that there exists a y such that for all x, we have x plus y equals 3. Okay, so there exists a y so that for all x, we have x plus y equals 3. Okay, I'm being a little bit interpretive here about how this says, what this statement says. But if I wanted to read it literally, it says there exists a y for all x such that x plus y equals 3. So there exists a y for all x such that x plus y equals 3. So if you wanted to be 100% strict on how you read that, but this is the meaning of it. We want to know, does there exist a y so that for all x, we have x plus y equals 3? And this statement is false. There is no y value such that for all x, you have x plus y equals 3. And to prove that this is false, again, you have to, to prove a for all statement, to prove that there exists statement is false, you have to justify it somehow. And so here, I think the easiest way to justify it is a proof by contradiction. And I'm not going to write out the details, but suppose there was such a value. Okay, so suppose there was such a value. If that value is, say, 2, then so suppose that the value that you're looking for y, the magic y value is 2, then that's not going to work because you could pick an x value that's not 1, say 0, and then 0 plus 2 is not equal to 3. So it can't be that the y value is 2. It also can't be that the y value is not 2 because if the y value is not equal to 2, then you could pick x equals 1 to be your counterexample. And that means that there's nothing that you can do. There's no value of y that you can pick that's going to work. In other words, there is no y value that'll work. So that's a wordy proof. I'm not gonna write that out in detail. But I want to pay attention to the order in which our x's and y's are chosen. Notice that in the first example, we picked x first. So you pick whatever value of x you want, and then once that happens, then we can find the value of y, such that x plus y equals 3. Okay. On the other hand, here we're going to pick y first. We want to know, does there exist a y value that we can pick ahead of time so that no matter what x value we pick, we have x plus y equals 3? And the answer, of course, to this last question is no. There is no y value you can pick ahead of time so that for all x's, you have x plus y equals 3. That just can't happen. Okay, and we kind of reasoned why that can't happen. So the order that we pick the quantifiers is going to be very important for us. In our case, it actually changed the truth value. And so we just have to be very careful about that. You could also have other mixed quantifiers. So one of the first quantifier proofs that maybe you've seen is in Calc 1, you learn about what does it mean to say that the limit of a function is x approaches a equals L. And so what it means is that I'm going to write this now using quantifier notation. So we say that the limit of f as x approaches a is equal to L if for all epsilon there exists a delta such that if x minus a in absolute value is less than delta, then f of x minus L is less than epsilon. So notice that we're saying a whole lot in that one line. Writing symbols and these mathematical symbols is a concise way to get our point across, but we lose a little bit of meaning. We have to kind of interpret this now. We have to be very careful about the order that we're picking everything. Okay, so I think this is a good example of a mixed quantifier statement, something that you've inevitably seen in Calc 1 before. I'm not going to do any examples of epsilon delta proofs, but this is a good example of a for all there exists mixed statement. Okay, so next what we'll do is, I think we're now ready to start talking about some mathematical proofs.